Hello everyone, welcome to this lesson. So in this lesson we're going to start the second branch of root finding techniques, which is open methods. And basically we're going to be starting the first method within that, which is the Newton-Raphson method. Now if you remember, in previous lessons we have covered the bracketing methods, which involve two guesses that bracket the root, and we have covered the bisection method and also the false position method. Now the Newton-Raphson method is known to only require one guess, which is why it's called an open method, because it has the tendency, or not the tendency, the possibility of diverging. So the way I'm going to be describing the Newton-Raphson is we're going to be going through three iterations of the Newton-Raphson, and we're going to describe how it actually finds the roots, and also we're going to be deriving the equation for it, which is actually very, very simple. So actually, let's for instance take the guess for the root initially is 1. So I'm going to guess the root here is 1, as you can see here. And what the Newton-Raphson does, it takes the function value at that x value, and it actually uses its derivative at that point, and where the derivative actually intercepts the x-axis is our root. So you can see we actually took 1, and the derivative here using this point where it actually intercepts the x-axis is actually 3. So the first estimate for the root is now 3. So what the Newton-Raphson goes and does again is that it takes the function value at that new estimate, which is now 3, as you can see here, takes the derivative, and actually where it intercepts again becomes the root. And here it's 2.2, and it does it again, takes the function value or the derivative at that function value, and the intercept of that derivative at the x-intercept becomes our root, which here is 2.012. Now, let's actually create a equation for xr, and it's actually very, very simple, because we're going to be using the equation of this slope, and the equation of this slope is rise over run, and you can see that the rise here is f of xi, as you can see, divided by the run, which is basically xi minus xr, which you can see here. And if we rewrite this equation in terms of xr, we get this expression that is in terms of the guess, which is xi minus the function value at xi divided by the derivative at xi. So let's actually take each one of these three iterations and actually get actual values for it. So if you see here, the guess is 1. The function value at 1, as you can see, is -2. And the derivative here is 1. And if we actually solve this, now it's going to give us an x-intercept of 3, as you see here. Now, since the actual root is 2, that gives us a 50% error. And let's actually go to the next one, where basically now our guess, or the estimate that we have currently, is 3. The function value at 3 is 4, and the derivative at 3 is 5, which gives us an intercept of 2.2. So now we went from a 3 to a 2.2, which gives us a 10% now true error. Let's do it one more time. Now we're going to use the estimate at 2.2. So we're going to take here xi to be 2.2. The function value at 2.2 is 0.64, and the derivative at 2.2 is 3.4, which gives us an x-intercept, or the new estimate of the root, at 2.012, which gives us a true error of 0.588%. So you can see that it's in just 3 iterations we have a root estimate that has accuracy of 0.588%. So you can see it's actually a very effective technique, and it's also a very, very simple technique. It just uses the derivative at whatever point you're interested in, or whatever guess you choose, and it just basically extrapolates it to getting the x-intercept, and it keeps doing this until it diverges, or it converges to the true root. So in the next lesson, we're going to be creating a Python code for this, and you're going to find that actually the Python code for the Newton-Raphson is a simpler code than the false position and the bisection, because if you have noticed here, we did not have to choose which interval we need for the upper lower limit as we did for the bisection and the false position, which means we don't need this section of code and it's going to be eliminated. Well, that's it for this lesson, and I will see you in the next lesson.